In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 7, Elastic Plastic Analysis of Thick Vessels Under Pressure and Temperature Loadings, Part 2. In Part 1, we discussed this spherical vessel, thick, hollow spherical vessel. Inside it is empty. It has a wall thickness which is comparable with the inside radius, and we considered such a sphere under the action of internal pressure, and we derived the stress distribution, strain distribution, the displacement relationship along the radius, and also we developed some relationships for the incipient yielding, which we determined that it happens at the inside wall. And in this case, we have this thick sphere, and inside the thick sphere we don't have any internal pressure. Instead, we have a source of heat. Okay, it may be a liquid or a fluid with high temperature. So that is the source of heat, and that source of heat gives rise to the temperature difference across the wall thickness. Okay, and so we get different temperature at different places, and that sets the stresses in the sphere at radial and hoop directions, and therefore we get some strains due to those stresses. So strain in the radial direction, we use the elastic relationship. These are the stresses due to the temperature difference. Also we get an expansion, obviously, which is to do with the coefficient of expansion, alpha times T. That gives the displacement. So gives the strain. So the strain in different directions, we get different values of stresses. And now for this equation, we can write it like this. Epsilon R is equal to partial U to partial R. That's a general relationship for epsilon. And therefore that is equal to this. Because this sigma theta and sigma phi we said are equal due to the axial symmetry of the sphere. And similarly for other equations. For this equation, for instance, we get this, and for this one as well. Epsilon theta equal to epsilon phi, U divided by R equal to that one. Here again, phi and theta are equal, sigma theta, sigma phi are equal, so we write it like that. And then from here, we could take partial differentiation, partial of U to partial of R, and multiply R by this. So first multiply R by this equation, and you get U equal to R times 1 over E, etc. And then take the partial of U to partial of R. Okay, so you get this relationship from here. R times the partial differentiation of this part, and then we got this R alpha times partial differentiation of T with respect to R, and then partial differentiation of this times R, which partial differentiation of R relative to R is 1 times this part. Therefore, if we do the partial differentiation of this one, we get this relationship, and we already had this relationship. So we put these two equal, so this relationship is equal to that relationship. So from similar to the internal pressure, we did the same thing. So we bring the other terms over here and put the total equal to 0, and we can simplify this relationship is simplified to that due to this, because sigma theta minus sigma r is equal to this. This equilibrium equation remains the same as before because we derived this equilibrium equation from first principle on an element of the sphere. So never mind what the loading is, since the element is in equilibrium, the equation is the same. So that's the equilibrium equation, and we substitute for sigma theta minus sigma r from here to there, and we get this equation becomes this. So we have this equation from the previous page. If we simplify that, we can write it down like that. This relationship is similar to what we had before for the pressure loading, but here we have temperature loading, so that we get this temperature item in here. So that is the compatibility equation, and we can go ahead just like before. But before doing that, if the temperature inside the sphere is equal to T, then the temperature at the walls at A and B, we call it TA and TB, and we assume that the relationship is something like that. So T is equal to TB plus TA minus TB, B over R minus 1, B over A minus 1. If we put R equal to A, then that fraction becomes equal to 1, and then TB minus TB cancels out, and T is equal to TA. If we put R equal to B, then that's 1 minus 1 is equal to 0. 0 times that is 0, so T is equal to TB. So that's the boundary condition is applied correctly, and this relationship has been assumed for the temperature distribution between TA and TB. Of course, we can assume different kind of temperature distribution between TA and TB, but this is some kind of linear relationship. We usually use this kind of things. And for simplicity, because we want to simplify our equations, we assume another parameter beta is equal to alpha times TA minus TB divided by 1 minus mu. Okay, because we have 1 minus mu here, and we are going to use this TA TB, so that's why we assume this relationship so that we can simplify our equations. And therefore, that equation becomes equal to this if we integrate it. So if we integrate this equation, we get sigma r plus 2 sigma theta plus 2e alpha t divided by 1 minus mu, and considering this substitution, we get that becomes equal to this, and this a is the constant, 3a in fact is the constant of integration, just like before. Okay, so this is the equilibrium equation which we had before, and from these two equations we can get sigma r and sigma b by integrating this, so that we have this a plus b, a minus b here, just like before, but the relationship is different here because we have temperature distribution, a temperature source, heat source, and we put these boundary conditions. R equal to a, sigma r again is equal to 0, okay, because we have no pressure or anything in here, and so that is the stress here is 0. That's the free surface also, in here, so the stress in there is also 0. Therefore, if we put these boundary conditions into the previous equations, we get A and B equal to that, and substituting back for A and B in those equations, we get sigma R equal to this relationship, okay? And also we get sigma theta is equal to this relationship. As you can see here, we have this beta, which is in terms of T, and R, which changes between A and B. The rest are constants. Of course, here we note that we have R here and R cube here as well. Here we have an alternative method of solution to get the stress distribution like this. Epsilon R is the partial differentiation of U to respect to R, and we also had it at the beginning of this part. We showed that epsilon R is equal to this. Therefore, I can write down sigma R in terms of this. Okay, I can write sigma R is equal to 2 mu sigma theta minus alpha T E plus epsilon R E. Therefore, if I multiply this E by epsilon R, I get this sigma R. And if I substitute for sigma R in here, okay, substitute for sigma R in here, I get epsilon theta equal to this relationship, right? And I can use this relationship by multiplying this E times epsilon theta. E times epsilon theta is equal to that, and bring some terms to the left of the equation, take some terms into the right of the equation, and I obtain this equation from here. Okay, so in here you can see that I have substituted for sigma R. Therefore, this equation is only in terms of sigma theta. No other sigma is in here. So I can write down sigma theta is equal to this. So sigma theta here is written in terms of epsilon theta and epsilon R, as shown here. Now, I had before epsilon R equal to partial U to partial R, and epsilon theta is U over R. So if I substitute these in here, okay, and also in here, okay, I get these two equations. Sigma R and sigma theta are these two. So I substitute for epsilon theta, epsilon R from these, and as you can see here, everything is in terms of U. Sigma R and sigma theta are in terms of U, but I have U, partial U, therefore I can integrate it. Okay, so this is it. Now, in order to obtain sigma theta and sigma R, I use the equilibrium equation, which was this, the same as before, and therefore here I can substitute sigma theta, and here I can substitute sigma R. And if I'll do that, then also I have to substitute partial sigma R to R from this equation. If I do all of that and simplify it, I will get the equation in terms of U displacement only. And if I get the displacement U, then I can substitute here and get sigma theta and sigma R. And so if I want to get U, I have to integrate U with respect to R. If I do that, I will get some constant C1 and C2, and I have to use the boundary conditions. R is equal to A, sigma R is 0, R equal to B, sigma R is 0, because before we had internal pressure, then that was equal to minus P, but we don't have any internal pressure, so it's 0, no pressure outside 0, we have only temperature, no loading on the free surface. And because of that, I had before this sigma R and sigma theta in terms of constant C1 and C2, so I put these boundary conditions, I get the constants. Still I have to do some integration in terms of the temperature, so I use these boundary conditions for the temperature, and this is T equal to alpha E Ti over 1 minus mu B over R minus 1, and therefore I can integrate this these two, and I will get this sigma R equal to this, and sigma B is equal to this relationship. Okay, so this is the alternative solution that I'm explaining, and therefore simplifying, we get the same equations as we had before, and substituting in the strain distribution, we get a substitute for sigma theta and sigma r, and considering this u divided by r, we get this relationship. Therefore we have u from here. Okay, u from here, and now let's go to incipient yielding. So these are the stress distributions due to the temperature only. Okay, and we know that Tresca and Mises yield criteria here are the same because due to axial symmetry. Therefore sigma theta is equal to minus sigma r is equal to y. And here, if we substitute for these, just note that if beta is greater than 0, then the temperature inside the sphere will be greater, and if it reaches a critical value, yield starts from the inside surface. Okay, so if the temperature inside is such that beta is greater than 0, that is constant, so Ta minus Tb is greater than 0, Ta greater than Tb. So if Ta or Ti is increased to such an extent that these stresses increase such that sigma theta minus sigma r becomes equal to y, then yielding starts. Okay, incipient yielding starts. Now we have this sigma r minus sigma theta equal to this. If we subtract this from that, we get this relationship. Okay, we get this relationship. It could be seen that the maximum value of the above expression again occurs at r equal to a. Why is that? Because all these values are constant here except r. Okay, so this is, we have a r cube here and we have r here. So this denominator, if we put r, then this will be a very small value. Okay, minus another small value gives us the smallest value possible to reach y. So we say that the smallest value is r equal to a. So that's why we say it happens at r equal to a, and we put beta equal to beta y because beta represents t. So if beta reaches beta y, Ta reaches ty, and then this one in here, beta y equals y over e times this relationship. Therefore, in order for incipient yielding to occur, beta y must reach that value, and it means that Ta minus Tb must reach that value in order for the yielding to occur from A. As the temperature increases, the yielding progresses towards B.